Okay, yeah. So this time we go over the very technical definition of. Okay, so maybe let's go back a little more. Okay, 10. We go over this very technical definition. Where am I stuck? Okay. Close. This is weird. So space. Even. Okay. Maybe here. And oh, it's still here. Okay. Yeah. We go over this very technical definition of a vector space, and so we say vector space is a set of things, hopefully are vectors, and so it's a set with two operations, addition and scalar multiplication. So you should take so scalar multiplication says you take everything in your set, and you can multiply a scalar on it, and it will give you something. And addition is you take two things in your vector space, and then there is an operation that define addition on it. Then it will be something, and hopefully both of those something are in your vector space. We have seen an example where you can define both addition and scalar multiplication operation, where those operations get you out of the space. It's those thing with it's just here, right? If you define your space being this A1, then you define your addition and the scalar multiplication by just usual matrix multiplication and addition, then you will get out of your space. Okay, so a vector space is a set with those two operations, and they need to satisfy 2 plus 8 properties. So first, they need to satisfy those two closure property. And then addition and scalar multiplication need to satisfy these additional 8 properties for your space to be a vector space. And yeah, so there are a lot of properties here, but mostly this is what you expected for your space to be linear. Okay. Yeah. And notation, then we go to, okay. Then we go to this, things a little trivial but actually pretty hard to prove theorem. So theorem 3.1.1, so first says the scalar multiplication of x, 0, scalar multiplication of 0 on any vector x give you the 0 vector. And then there's a 3, and the second one it says this, this inverse of this inverse of vector addition is unique. The third one says that -1 times your vector is inverse of your vector. And we go through this thing. This is a show of things you need to be very careful when you do this proof from accident, because a lot of things that you might think trivially true is not quite true. So we need to go through those 8 properties carefully to prove that. So the first one is the hardest, so you need to prove that 0x is actually equal to 0 vector. So we had a big example here saying that so things like subtraction you cannot even do with just the axiom without proof 3.1.1. because you don't know 0x plus -1 or 0x equal to the 0 vector, etc. Okay, because this requires the third one, which we use for the first one to prove. Okay, and okay, so that's vector space. Then we go to subspace. So subspace is a subset of your vector space. That's also a vector space itself. And we have this kind of a small theorem. Yeah, and we have basically a small theorem says that you only need to check closure. So subspace, important thing is, so subspace is a subset of the vector space, and it also has scalar multiplication and addition, but it being a subspace of a vector space, the scalar multiplication and addition should be same as the parent vector space. So S is a subset of V, then the scalar multiplication of V of S and the addition on S should be the same as that of V. And if you use this scalar multiplication and addition and it's still closure in S, then we say S is a subset. And where do we do that? Yeah, and so and as we said, being a vector space need to satisfy 10 properties, and so there's 2 properties satisfy closure, and you need to check the other 8, and there are 2 of them that's a little more tricky to check. That's you need to check that 0 is inside S and minus X is inside S, and those 2 you can use theorem 3.1 to check, because we know with a closure, then we know that 0 times X is inside S, and from 3.1.1 also know this is a 0 vector. So 0 vector inside S, and similarly for the inverse. Inverse is minus 1 times X. And the other 6 property is just follow from their property in V. Okay. So that's subspace, and then we talk about 2 subspace. That's interesting. Okay. 2 subspace, and the first one is null subspace. Null subspace of a matrix is is a subspace in this X. So we are thinking about solving X equals 0. So the set of all those X that equal to 0, when you solve X equals 0 for some particular A, is called a null space of A. And okay, so that's pretty cool. And the other thing that we are going to use a lot today, well, we are going to see more detail of it, is the span of whole bunch of vectors. So you can get a whole bunch of vectors, whatever vector v1 to vn, that's in your vector space. Then you can consider a set of all those a1. Okay, it's alpha here. Alpha 1 v1 alpha 1 times v1 plus alpha 2 times v2 plus all the way to alpha n times vn, where those alphas are scalar, and we say all of them means that we pick all possible value of those alpha. So alpha are real, so they are all from infinity to infinity. So we consider all those in linear combination, and the set of all of them is called the span of those vectors, and we write it as a span. And it's a subspace. So we can prove that we prove. And finally, and oh, okay. Yeah. So null space and span, and finally we have this theorem 3.2.2 says that so when you want to solve A is equal to B, and basically when you have infinite, although this is true for every kind of solution, is whenever it's consistent. So whenever it's consistent, then A is equal to B can be written as this X can be written as some particular solution X0 plus this interesting homogeneous solution. So Z is the solution of AZ equal to 0. So you can plus any solution to AZ equal to 0, then you will get another solution to AX equal to B. And the proof is here. And this is actually if only if. And yeah, so here you can also get some derivation. So if you only have one solution, then that means AZ equals 0 must only have the trivial solution. Okay. And anyway, that's a quick review. Any question? Otherwise, we will talk more about span. We'll analyze. Today, we'll spend the whole class basically analyzing property of a span. Okay. And the property is called linear independence. And so what do we mean? Yeah. So if we have vector space spanned by some vectors, then obviously, by definition, every vector in your vector space can be written as the linear combination, right? And but so span has a lot of vector. Okay. Anyway, yeah. So span can have a lot of vectors, but we don't want to write down. Sorry, not span has a lot of vector. So span is built from a lot of vectors, right? So it's usually like v1 to vn, and but sometimes. But we want to keep our writing as little as possible, so we want to find like a minimal spanning set. So maybe we don't need to v1 to vn, maybe we only need v1, v2, etc. We got v1 to vn minus 2. And so one thing we want to find, although that's more important for next class, but we'll talk a little here, is we want to find the minimal spanning set. So can we get rid of, so we have this v1, v2 to vn, right? And so maybe vn. And so we want to like, one thing we want to do is maybe we want to get rid of this and get rid of that. And we want it to still span v, okay? Kind of this thing. So like how many of those vectors can we get rid of? Well, we still span the whole space V. Okay. And yeah, and we'll see that it actually depends on how those vectors depend on each other, linearly depends on. Okay, so that's why we have linear independence and a linear dependence. So maybe let's see an example first. And so we have those three vectors in R3, x1 equals this, x1, x2, x3 equal to those. And we consider some subspace spanned by all those three. Okay. And but now we see what a linear dependence is. So we see x3 actually have linear dependence of x1 and x2. What does it mean is that you can build x3 by doing a linear combination from x1 and x2. So check the math. Hopefully this is correct. And yeah, so you do 3x1 plus 2x2 and you find out that's x3. Okay. And yeah, so x3 has linear independence from x1 and x2. Then we think about we want to span some space S from x1, x2, x3. Then x3 is actually pretty useless, because say you want to write some alpha1 times x1, f2 times x2 plus alpha3 times x3. Then this alpha3 times x3 you can written as a linear combination of x1, x2, right? And so everything can be just written as a linear combination of x1, x2. Okay. So yeah, so here example of we can get rid of one of the vector and still span the same space. The span of x1, x2, x3 equal to span of x1, x2. Okay. Question? So yeah, this kind of phenomena is what we'll analyze this whole class. Okay. And yeah. Okay. And let's write this. Let's write this in a more symmetric form. So we have this equation, right? So we see the best thing happen because of this equation, x3 equal to 3x1 plus 2x2. And we can actually write this in form that's symmetric between x1, x2, 3. So you just move the x3 to the left-hand side. Then you see we have this equation, 3x1 plus 2x2 minus 1x3 equal to 0. Okay. And yeah, and then we can move things around, so we can actually use this equation to express any one of them, any one of x1, x2, x3 as a linear combination of others, right? So like x1 equal to, so you move, so you move x2, x3 to other side and divide by 3, then you get the x1 equal to linear combination of x2, x3. Then you can do similar things, so move x1, x3 to other side and divide by 2, then you got x2 equal to linear combination of x1, x3, etc. Okay? So yeah, although this is not too important, but here you see that you can get any one of them, and you still span the whole space. And that's all because you have this dependency relationship between x1, x2, x3. And we will write a lot of things in this form, so like some scalar times your x1, scalar times x2 plus x scalar times x3, and equal to 0. Okay, we want to write some linear combination of things in your span, and they equal to 0. Okay, and yeah, so more generally, okay, not actually more generally, a little more specific, because now we consider only 2 vectors. So consider we have 2 vectors in your span, so like this x1, x2, and okay, and I guess we consider. Oh, okay, sorry. The logic here is this. Okay, so we consider we have span x1, x2, 3, and and we get rid of x3, and now we have a span of x1, x2, right? So we still consider those in x1, x2, x3. So we now have a span x1, x2, and we are thinking whether we can keep one of them out and still span the same space S. Okay, and yeah, and we try to check this equation. And want to see if there is some C1 and C2 not equal to 0, not all equal to 0, such that C1 x1 times plus C2 x2 equal to 0. And if we can, then we can write we can solve either one of those if one of them is not 0. Okay. So we can either write x1 as a linear combination of x2 or x2 as a linear combination of x1. We need to write separate them because one of them might be 0 and we cannot divide by 0. Okay. And but now we check out x1, x2. Okay, so x1, x2 we had before. So this thing, they are not the multiple of each other. It's easy to see. Okay, so we cannot have this. Yeah. And yeah, so we see that. Well, it's a little different thing, but we see that this equation holds only when C1 and C2 equal 0. And so what do we see here is when we consider this span x1, x2, we see that x1 and x2 are not linearly depend on each other, kind of because you just check that x1 cannot write as a linear combination of x2, and x2 cannot written as a linear combination of x1. And we see that these x1 and x2 are linear independent is same as C1 and C2 must be 0 when you write this equation. Okay, so that's something we'll say a little more later. Okay, so I guess here is the summarization. Okay. And okay, so first thing is about how we get the minimal span. So we have some v equal to, okay, so maybe let's write down equation. So v equal to span of this small v1 to small v2. Sorry, small v1 to small vn. So v equal to span v1. Wait, where's your notation? I forgot. Okay. Okay. Sorry. Span parentheses span v1, v2 to vn. Okay, and now we are thinking we want to get rid of some of them, and we see that we can get rid of some of them if although we didn't prove, or we'll prove it later. Yeah, and we say we can get rid of some of them if if some of them can be written as a linear combination of others. So for example, Vn can be written as a linear combination of others, then we don't really need Vn. And the second one, the condition that you can find some of them that are written as a linear combination of others is this equation. Okay. This equation is very important, going to see it all the time today. So if you can write C1 plus V1, C2 plus V2, all the way to Cn plus Vn equals 0, this is 0 vector. So you can find some linear combination of those vectors equal to 0. with non-trivial assignment of C1 to Cn. So obviously, if you take C1 to Cn all equals 0, this will equal 0. But if you can take a sum of these not all equals 0 and it's still 0, then we know there is some linear dependence between this V1 to Vn. Okay, so once again, for this example, we have 3x1 plus 2x2 minus 1x3 equals 0. Then we find out that, say, we can write x3 as a linear combination of x2, 1x2. Okay, and I guess let's go to proof. So we have a proof of those two things we can. Okay. And the first one is if we can write one of them as a linear combination of others, then you don't need it. You can get rid of it and still span the same space. Okay. And so without loser generality, let's assume Vn is the one that can be written as a linear combination of others. So Vn is written as this beta times all other V's. Okay. And so the proof is pretty trivial. Suppose, just like before, suppose there is some vector in V. It's a linear combination of this V1 to Vn. And then you can just replace this Vn as a linear combination of V1 to Vn minus 1. And then we still have this linear combination of V1 to Vn minus 1. And then we have a linear combination plus a linear combination, still linear combination. You just add together the coefficients. So here we have alpha 1 and alpha 1 V1, and here we have alpha n times beta 1 V1. And so it just becomes alpha 1 plus alpha n times beta 1 of V1. Okay. And so you see all the coefficients add up, and it's the same thing here. Okay. So we prove that if Vn can be written as a linear combination of V1 to Vn minus 1, then everything in V can be written as a linear combination of V1 to Vn minus 1. And so that's our claim. So V is a span of V1 to Vn. Okay. Any question? That's a concept that's, well, it will be more important next class, but it's something that we want to learn today. That is, when you have a linear dependence between these vectors, then sorry, I keep saying linear dependence although I haven't defined it. So I should say, so if one of them is a linear combination of others, then you can get a derivative of it and get a smaller spanning set for your vector space. Okay, so that's one. And the second one is, well, we're getting closer to linear dependence and linear independence. And it says that it's possible to do the one thing, so one of them is a linear combination of others, if only if, when you write down this equation, so linear combination of them equals 0, and you have non-trivial C's. Okay, so it's if only if, so we need to prove two directions. So first we say if, when there is some linear combination of them, one of them equal to linear combination of others, then you can write non-trivial of this solution. And it's pretty easy, so you just write down. So once again, let's assume the one that being linear combined is this Vn. So Vn once again equal to this alpha times V's together. And then you just move this Vn to other side and you write down this equation. Okay, so this is already in the order C times V form. And why is this non-trivial? Because we have minus 1 here. Okay. So the coefficient of Vn is minus 1, and minus 1 is not 0, so we know those are not all 0. Okay, so it's pretty easy. And the other direction is also pretty easy. So you have this, and it's not all 0, and just pick the one that's not 0. And once again, let's say it's Cn. So you move Cn to other side and divide everything by minus Cn, and you got this equation. So you see Vn is a linear combination of others. Okay. And I guess that's straight again. Why we won't need non-zero here? Because you need to divide by Cn, and you cannot divide by 0. Okay. So that's the proof. Okay, finally we can talk about what's linear independent. And well, linear independent, okay. And so here, I guess let's go logically a little carefully. So linear independent, we want to say linear independent is you cannot do this thing. So you want to say linear independent is you cannot write any one of them as a linear combination of others. Okay? And but because of these two properties, so we just say linear independent is when you write this equation, all the c's are 0. Okay? And let's go skip ahead a little bit. And so that's linear independent, and there is linear dependent. And the linear dependent is you can do this thing. So you can write the v1 to vn. So some of the vn, some of the v, maybe vn can be write as a linear combination of others. And as we prove here, that means this summation, the c times v summation equal to 0 has some non-trivial solution. So yeah. So if this so linear dependent means you have a linear combination, and that means you have non-trivial c here. And linear independent means you cannot find any linear combination to each other, and that means all those c must equal to 0. Okay, so yeah, that's the most important concept here. And also skip ahead by just talking here is we see that if we have a linear dependent, then by 1 here, right? So 1 is talking about what happened on linear dependent. So 1 says that if your v1 to vn is linear dependent, which is equal to this as non-trivial solution, then you can just get rid of that one of the say vn, right? So that's what we prove here. So you have a linear dependent, and one of them can be written as linear combination of others. Then you can get rid of it and get still the spanning set. And remember from very beginning we said that we want to find the minimal spanning set of v. So we want to keep getting rid of those v's, okay, until we cannot get rid of any of them and still span the v. But we know if they are linear dependent, you can get rid of one of them. You can keep getting one of them. And vectors, because from this characterization you see that they are either linear dependent or they are either not linear dependent. Sorry, they are either linear dependent or linear independent. And if it's linear dependent, you can get a smaller spanning set. So the minimal spanning set must have linear independent v's. Okay. And yeah, so I just talk a lot of slides in right now. Let's go through them slowly now. Okay. And yeah, so as we said, linear independent means that so we'll define linear independent with this equation. So if c1v1 plus c2v2 plus 2 the way to cnvn equal to 0, if this equation only have the trivial solution c1 equals c2 equals cn equal to 0, then we call the v1 to vn as linear independent. Okay. And okay, so here is the thing that we say that yeah. So as we say, we want to find, okay, I should put this a little later, but anyway. So as we say, we want to find a minimal spanning set. That means we cannot remove anything from the set anymore while still span the same thing. And then as we say very long, then v1 to vn must be linear independent for this to be a minimal spanning set, because we know if we have this, we are proving this kind of a negative way. So because we know if they are linearly dependent, then we can remove one of them. Okay, so it's not minimal. Okay, can remove one v. Okay, and and this is actually also true in the reverse. And proof is a little annoying, so I think the proof is also trivial, so let's skip it. And also, so we know if it's minimal, then it must be linear independent. And we can also show that it's linear independent, then it's minimal. Okay, so it's a pretty cool thing, and yeah. So I guess left out the exercise to prove this. So exercise. Proof. I didn't have a proof here, but yeah. Yeah, and this minimal spanning set, so this is something that we'll talk about more next class. It's called basis. And yeah, so this should be the end of we talking about minimal spanning set. Okay. And yeah, we will focus this more next class. Yeah. For now, let's just remember that minimal spanning set means that the set is linearly independent. That's important to remember. And the intuition is that if you are not linearly independent, then then you can remove one of them. Yeah. And wait. Yeah. And so it's not minimal. So if you're not linearly independent, then you are not minimal. Then so you know it's minimal, you must be linearly independent. And yeah, the other thing. Okay, and let's finish this minimal discussion, and let's go back to just linear independence and linear dependent. Okay, so let's see some example. So vector 1, 1 and vector 1, 2, and want to see are they linear independent or linear dependent. And so as I say, we want to check these equations of c1 x1 plus c2 x2 equal to 0. So we brute force solve this, and we wrote down those equations. So once again, we get a linear system. So c1, so we check first coordinate should check, and the second coordinate should check. So c1 plus c2 should equal 0, and c1 plus 2c2 equals 0. Then you solve this, you find out both of them are 0. Okay. So we only have this c1 equals c2 equals 0 solution, so they are linearly independent. And then, as we say, we also have definition. I should reorder this. Yeah, we also have this definition that says they are linearly dependent. Then this solution has this solution to this equation. When you solve, okay, so solution for C1 to Cn has non-trivial solution. So you can assign non-zero C1 to Cn. I should not say non-zero C1 to Cn. So you can assign C1 to Cn that are not all zeros, and satisfy this equation. Okay, this is linear dependent, and here we get a linear dependent example. So we have 4 vectors in 3-dimensional space, and so first 3 is okay. So the first one is 1, 2, 3, and then we have the standard basis elements. Okay, although we haven't said what is standard basis, but we have those standard spanning set. Okay, so this is 1, 0, 0, 0, 1, 0, and 0, 0, 1, and obviously you can write everything in linear combination of this. And yeah, so you write this C1, 1, 2, 3 as a linear combination of others. Then then you find out that you just need to have it's a little weird, C1, C2. I think the solution here is a little wrong. So C1, okay, textbook has this wrong. Okay, so anyway, yeah, you can easily solve for this. So you have C1 here, and you can have C2, C3, C4 to cancel all of them. And I think it should be, why is this order so weird? So C2 should equal to -1, and C3 should equal to -2. And C4 should equal to -3. Well, I'll be wrong here. Am I correct? Yeah, I think I'm correct. Okay, yeah, anyway, it's easy to solve, just the number is wrong here. Okay, so yeah, so you can find a trivial solution of this down to 0, and so they are linearly dependent. Okay. So see, we can write linear dependence in this weird sum CIXI equal to 0 equation. Okay. And yeah, once again, we want to find non-trivial solution because there is a trivial solution of overlay equals 0. And then we write back again and then we say, so there is a linear dependent and a linear independent. We keep saying this many times. It's because they are very important. Okay. So there is a linear dependent and a linear independent. And we are characterizing them by saying you try to solve this C1v1 plus C2v2 plus all the way to Cnvn. You see if they have a trivial solution. If you have a non-trivial solution, then, to see if they have a non-trivial solution. So if they have a non-trivial solution, then it's linear dependent, and if they don't, you only have 0 solution, then your vectors are linear independent. Okay? So there are only 2 possibilities. You either have non-trivial solution or you don't have non-trivial solution. Okay, 10 minutes. We're a bit slow, so maybe we cannot finish, but it's okay. I think I was still pretty good on our progress. And anyway, let's go to some geometric interpretation of linear dependence. Okay? So in 2 dimensions, if you have 2 vectors, then linear dependence looks like this. So they are on the same line. So you have some x1, x2, and y1, y2. And then you have the c1x plus c2y equals 0. That means one of them is the linear combination of the other one. Is a multiple of the other one, so they should be on the same line. And they are linear independent, and they have these 2 different angles. And so you see they will span everything, and here you only span 1 line. Okay, so we are talking about linear dependence. So we're not talking about span for now. Okay. Yeah, and as we say, if they are linear independent, then they are not on the same line. Okay. If they are linear dependent, then they are on the same line. Okay. Okay, and well, we write back and say that it will span a plane. Okay. And then we have a 3-dimensional example. So here we can get some feel of linear dependence, and y is kind of useless. So we have x and y and z, and we say z is a linear combination of x, y. Then z is in this plane spanned by x, y, right? So when we consider the linear combination of x, y, z, is adding this z doesn't do anything because everything is on this plane. So linear combination of them is on this plane. Okay? So if you want z to be useful to span the whole space, then we want to kind of z to stick over the plane like this. So you can either stick up or stick down, etc. But you want z to be not in this plane, and z is linearly independent of x, y. And then we see the span of x, y, z will span bigger spans than span of x, y. Okay? So that's a geometric feeling of this. Okay, then let's go to more example of things being linear independent or linear dependent. So we kind of see those 3 numbers when we talk about span. Okay, so I guess we can do a quick yes and no. Okay, so first one, so this is 111, 110, and 100 are they linear independent in R3. So if they are linear independent, raise your hand. And if they are not linear independent, raise your hand. Okay, so yeah, pretty good. So they are linear independent, and here we do this brute force solution. And we say, okay, so we just write down the C1, X1, C2, X2, C3, X3, and adding it to 0, and do the solve. And yeah, you solve for all 0, they are linear independent. Okay, and okay, and the second one, it is 101 and 010 are they linear independent or linear dependent? You think they are linear independent, raise your hand. Okay, and they are linear dependent, raise your hand. Okay, yeah, it's actually linearly independent, although when we say span, it doesn't span the whole space. But those 2 things are linear independent, independent and less span the two-dimensional space by themselves. Okay. So yeah, so want to solve a summation of those two equal to O0. Then you take this, you see you have this C1, C2, C1 here. And although this is not everything in a two-dimensional space, but when you try to solve this all equal to 0, you still only have C1 equals C2 equals 0 solution. Okay, so this is linearly independent, two of them. Okay, and then finally, okay, so now we can actually solve this because you remember some solution of this before. And yeah, so those three vectors are linear independent or linear dependent. You think a linear independent, raise your hand. And if you see a linear dependent, raise your hand. Okay, yeah, so this is actually linear dependent because want to solve, once again, is C1x1 plus C2x2 plus C3x3 equals 0. And we write down the equation is like this. So it's a linear equation actually on C1, C2, C3, right? And you see the coefficient matrix is a matrix that's formed by those things. Okay. So basically you want to solve for we're jumping ahead a little bit. Yeah, so we want to solve for this equal to 0. And this is the equation. As we've seen before, this linear equation is singular. The coefficient matrix of this is singular. So determinant is 0, and so we know it has non-trivial solution. So this is yeah. So it's singular. So we know C1, C2, C3 has non-trivial solution. So this is linearly dependent. Okay, and yeah. So you see that this is a very general form, and we can write the theorem here. So theorem 3.1, 3.3.1. Instead that we have okay, and it's important here we have n vector in Rn. Okay, so this n and this n must be matched. Only work here when n match. So we have x1 to xn. We have n vector in Rn, and then you can list them together into a matrix. So each one of them is a column vector, and then you just list them column by column, and then we'll form a matrix X here. Okay, and what this matrix will do is consider whether these vectors are linearly dependent, and that's if only if your x is singular, or is independent if x is non-singular. Okay. And once again, remember x is singular if determinant x equals 0. And the proof is basically this thing, but written out in more mathematical form. So we want to solve C1, X1. Oh, I forgot to bold case here. Okay. Those are all vectors. Okay. So C1, X1, C2, X2, etc. to Cn, Xn. Those okay. We want to solve a summation of this 0. And if you write down in matrix form, so all those column vectors summation of 0. And and if we consider coordinate by coordinate, then the first coordinate will give you this C1 x11, C2 x12 all the way to plus Cn x1 equals 0, etc. And then you see this thing and you realize it's just your x times some c vector equal to 0 vector. The c vector has n dimension. Okay. Yeah, because this is like a linear equation of the C1 to Cn. So it's x times your c vector equals 0. Okay, so here's the tricky part. And yeah, then once you realize you are solving for this form, then once you realize, yeah, I guess you can also see from this just because you realize x equals 0 when your x is so x equals 0. We talk about this in matrix multiplication a little bit. So you can think about x equals 0 when you have x here, and you have the column as x1, x2, to xn, right? And you have c here, c1, c2 to cn. And so x times c, we said before that is a linear combination of all the columns. And yeah, so it's a linear combination of all the columns, as we said. Because x1 will get times by c1, x2 will get times by c2, etc. Okay. So anyway, this equation means x equal to 0 vector, And we want to find non-trivial solution on C, and that's if only if x equals singular, as we said before. And yeah, so x1 and xn linearly independent if only if x is singular. Yeah. And yeah, so here is just what we did before, and we just say again. So we form this matrix by listing the colors together, and see if determinant equals 0 means where the vectors are linearly independent. Now we have an example. And yeah, I guess we are just on time. But see here example, so we have 3 vectors, but okay, the example doesn't say too much. So you want to see whether they are linearly independent or dependent, and you list them like this, and if you want square matrix, and you calculate where the determinant equals 0. Determinant equals 0, then they are linearly dependent. Okay. And yeah. Yeah, I guess we are all out of time, but I can say very quickly. So those things, as we said, this theorem 3.1.1 only works when you can form a square matrix here. So a number of vectors need to be same as the dimension, and but what if the number of vectors doesn't match the dimension? So because the vector don't really need to match. Okay. And yeah, so if k not equal to n here, number of vectors not equal to the dimension, then you cannot really calculate determinant, because you only define determinant on square matrix. And yeah, and in this case, you need to do, well, basically similar thing, but then you need to go back to solve for row echelon form of x, and see if they have 3 variables. And you have 3 variables, then you have non-trivial solution and linearly dependent, and you have no free variable, then you you only have trivial solution and it's linear independent. And we'll see this more next time. Okay, and I think it's time for the class, so sorry for overtime. Any question? Otherwise, we'll finish this 3.3 next Monday, and yeah, and maybe get more on basics and stuff. Okay, and yeah, once again, we'll homework all later today. Okay, so see you next time.